dear students. This is the second lecture in module 1. The name of the module is state machine. So in the previous lecture, we have seen the introduction to uh, sequential logic circuits, and in today's lecture, we will explore the further topics. And agenda for discussion in this lecture is basically analysis of sequential circuits. Here we will explore flip-flop excitation tables and the state diagram associated with the flip-flops. We will discuss about uh, finite state machine, what exactly finite state machine is, its definition, and the types of finite state machine. And we will try to analyze the sequential circuits for which are being constructed using various types of blocks. As a learning outcome, at the end of this lecture, the learner will be able to explain the operation and excitation characteristics of SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop using their characteristic table, equation, and state diagram. The learners will be able to differentiate between the two fundamental type of uh, state machine. They are called Mealy machine and Moore machine based on their structure and their output behavior. They will be able to analyze the sequential circuit, rather synchronous sequential circuit using state table, state diagram, and flip-flop input-output equations. And they will be also able to determine the next state and output behavior of sequential circuit employed in different type of flip-flops. Let's proceed. First of all, we will have a discussion on the SR flip-flop details. So this is a table. In this table, as we can see, the first column is showing the symbol of the SR flip-flop, where we can see that the inputs are S and R and outputs are Q and Q bar, which are complementary in nature. And we can see that the clock is uh, clock signal, which is showing that this is a positive age triggered flip-flop. Only triangle is there. Next, we have the characteristic table or truth table, where we can see uh, that S, R inputs are there, and Q is representing the present state of the flip-flop, and Q next is representing the next state of the flip-flop when inputs are applied, and then the clock signal arrives at the flip-flop. So when the inputs are at 0, 0 condition, which we know that it is no change condition, so present state is 0. So obviously next state will be also 0. Similarly, when the inputs are at 0, 0 and Q is 1, so in the next state, Q will also remain 1 because the state will not change. The next one is the reset condition where S is equal to 0 and R equal to 1. So Q state, that is present state, whether it is 0 or 1, it doesn't matter. So next state will be a 0. This is true for reset condition. Similarly, when we apply set condition at the input, that is S equal to 1 and R equal to 0, irrespective of what present condition of the flip-flop will migrate to or remain into the set state, that is Q equal to 1. And in case of SR flip-flop, uh, there is a indeterminate or forbidden condition when S and R both are simultaneously 1. So this is a unusable condition, and normally we do not use this condition because output remains unpredictable. That's why a don't care condition has been applied. Now this is representing the state diagram of the SR flip-flop, where we can see
the SR flip-flop can be in two states, that is Q equal to 0 and Q equal to 1. So this circle is representing in the state Q equal to 0 and the another circle representing Q equal to 1. So if we see the characteristic table, we can see that uh, when the present state is 0, like here, and here, in these three conditions, present state is a 0, and but in these two conditions, the next state is also a 0. So what are the conditions? The input
is 0 0 here and input is 0 in 1 here. So in this both condition, if the present state of the flip-flop is 0, so it will remain to be in that state. So that is the self loop is indicating that. That means present state is 0, next state is 0. Under what condition? SR equal to 0 0 or SR equal to 0 1. Similarly, when the flip-flop is in Q equal to 1 state, that means it is storing a 1 during that time. So that can be represented by this state or this state or this state. So out of which, uh, when S equal to S and R equal to 0 0 or 1 0, as you can see, 0 0 is the condition, this one. So present state is 1 and next state is also 1. And here, if the present state is 1 and next state is 1, under what condition of the input? 1 0. So in these two both condition, present state is 1 and next state is 1. So that is being represented by this self loop, because in this condition S is equal to 0 0 and or SR equal to 0 0 or SR equal to 1 0. Now next we can see in two conditions, when SR is presently, the Q state is presently at 0, and when SR equal to 1 0, when SR equal to 1 0, so from present state 0, it will migrate to 1 under the input condition of 1 0. So that is being reflected by this transition, which is shown by the arrow. And if present state is a 1 and next state is 0, that happens when we apply input 0 1. So we are presently at Q equal to 1 in this state, and if we apply this input condition, then the flip-flop will migrate to Q equal to 0. So this is how the state diagram for SR flip-flop is being drawn. And these two equations are called characteristic equation for the SR flip-flop, where uh, this is the simplified expression. If we use this in a Carnot map and take S, R, and Q as input and Q next as output, then we will get this expression, the simplified expression from that Carnot map, or we can use Boolean theorems and laws to simplify this expression. Finally, we will arrive at this. And since we do not want the forbidden condition to appear at the input, so which ensures by the second expression. So these two expression or these two Boolean expression together is called the characteristic equation for the SR flip-flop. Now on the last column, we have excitation table. So in the excitation table, we have the present state and next state of the flip-flop outputs at the left hand side. And on the right hand side, we have the two inputs. So it shows that presence from a present state to a next state, under what condition this transition happens, all these are listed in the excitation table. For example, for 0 0, that means present state is 0, next state is 0. So what is the condition? As you can see in the state diagram, that when it is a self loop, the present state is a 0 and next state is also a 0. What are the conditions? Either SR should be 0 1, 0 0, or SR should be 0 1. So from here, S is common, whose value is 0, and R value can be a 0 or can be a 1. So in such situation, we put this as a don't care. So that means when S is equal to 0 and R is don't care, so what we understood is that the flip-flop present state is 0 and next state is also 0. Now similarly, if we see in the next row, over there we'll find the transition condition. Present state is 0 and next state is 1. Under what condition it happens? We have already discussed that SR should be equal to 1, 0. So similarly, other rows can be worked out for this in the SR flip-flop. So if we proceed further, then see for the JK flip-flop. Similar type of symbol where the name has been replaced now by JK. Then the characteristic table is also similar, except that the last two conditions, where in case of SR flip-flop, they were forbidden, that means they were represented by don't care. Here we have definite condition and usable condition. They are called toggle condition. Toggle condition means if the J and K both inputs are at 1, 1 and the present state is at 0, then it will migrate to the next state. And so as the case here, as you can see that present state is 0 and next state is present state is 1 and next state is 0. So these are called toggle condition, means whatever is the present state, next state will be just opposite of that. Now, this diagram explains the same thing, what we have understood in case of SR flip-flop. So the input conditions for the self loop also remains same for Q equal to 0, for Q equal to 1, this also remains the same. Only thing is that in case of transition from 0 to 1, in the previous diagram, we had only 1, 0 condition. Now we have 1, 1 condition over here, and same is the case over here also. So from here, in similar manner, using the Carnot map, we can find out the expression for what is Q next. So if we write all the expressions where Q is equal to Q next equal to 1, then from there also we can simplify and finally we can arrive at this expression, or we can simply use Carnot map to solve and directly getting this expression. So Q next, that is the characteristic equation for the JK flip-flop, is Q next equal to K bar Q plus J Q bar. And over here, the excitation table, here we can see that 0 to 0 transition is 0 don't care. Again, same condition we can see, which is similar to that of the SR flip-flop. 0 1 condition, that means present state is 0, next state is 1. So here it differs with the SR flip-flop because we can see that JK can be 1 0 or 1 1. So here 1 is common and for J, and for K, in one case it is value is 0, in another case it is 1. So that's why we get a don't care. Similarly for 1 0 condition, that means from 1 to 0 we are making transition. So during that time, the J value will be don't care and K value will be 1. And when it is 1 1, that means it is remaining at 1 uh, from its present state. So in that case, as you can see that it is don't care 0. So this is how the excitation table for the JK flip-flop is described. Next, we move into the D and T flip-flop details. They are more simplified version of SR and JK because both the flip-flops are having only one input. In case of D flip-flop, the input is D. As you can see, in case of T flip-flop, the input is T. So since there is only one input, we can see that if you apply a 0 at the D input, so the flip-flop output condition, irrespective of the present condition, in the next state it will be a 0. And if you apply a 1 at the input, so irrespective of the present condition, the next state condition will be 1. So here the state diagram is also quite straightforward. As you can see that if we are there in the present state with q equal to 0, then if we apply d equal to 0, we will remain over here. And under that situation, if we apply d equal to 1, then we will migrate to state 1, that is q equal to 1. And when we are there in q equal to 1, and if we apply a 1, then we will remain in the same state. And during that time, if we apply a 0, then we will migrate from q equal to 1 to q equal to 0. So this is the Boolean expression q next equal to d. That is, in case of d flip-flop, the output will be simply equal to the input d. And over here, the excitation table is also very simple. As you can see, 0 to 0 transition will happen when D is 0. 0 to 1 transition will happen when D is 1. 1 0 transition happens when D is equal to 0. And 1 1 transition happens when the input is 1. Similarly, here for T equal to for the T flip-flop, as you can see that here the characteristic table, if we put uh, T equal to 0 and Q is presently 0, so next state will also be 0. And if T is 0 and Q equal to 1, so then also it will remain in the present state only. That means it will not make any state change. But when we make T equal to 1, which is the toggle condition in case of T flip-flop, so then the next state will be just opposite of the present state. So the present state is a 0, that's why next state will be 1, and vice versa in the last condition. So here we can see that this is also similar to our uh, D flip-flop, but there are certain changes also. Like we can see that when it is, as you can see that when we are in state 0 over here, and if the present state is the input condition is T and our present condition is 0, then we will make a self loop. That means we will remain in the same state. And then when Q equal to 1, that means present state is 1. And if we have T equal to 0, then the next state will also be 1. So that means that is represented by the self loop. And they will migrate from one state to the another, like when Q equal to 0, Q equal to 0 and input T equal to 1, then it will make transition to Q equal to 1. And over here, from here to here, it will make transition, because that means from Q equal to 1 to Q equal to 0, it will make transition when T equal to 1. And from here, if we find out the expression, then we will find that this is the Boolean expression governing the relation between input and output in T flip-flop. And if we see the excitation table for T flip-flop, then here we will find that if both inputs are, if present input is 0, then next state will be 0 when t is equal to 0. So that we can see from this state diagram. It will make transition from 0 to 1. It will make transition from 0 to 1 when t is equal to 1. It will make transition from 1 to 0 uh, when t equal to 1. That means this is the situation, this transition it is referring over there. And when it is 1 1, that means present state is 1, next state is 1. So that means this is the state. So under that condition, t is equal to 0. So these are the details of the T flip-flop and D flip-flop, along with SR and JK flip-flop that we have come.
Talk about finite state machine. So here, uh, by definition, we can say that a finite state machine is a system that can be in only one of the finite number of states at a time and changes from one state to another when an input or event occurs. So, to give a good analogy, to our learners, I have taken the example of a table fan where, as we can see, that the fan is having three states. One state is called off state, next state is called low state. That means in this state the fan moves slowly, and there is another state called high state. In this state, the blade of the fan rotates fast. So when we connect the fan to the wall socket and switch on, it will remain on the off state. And when we press the button, then what will happen? It will make transition from the off state to the uh, it will make transition from the off state to the uh, low state as it is shown over here. Then thereafter, it will make transition from the low state to the high state again when we press the switch again. And thereafter also, if we press the switch, then it will uh, come back to the off state from the high state. So this can be represented in the form of state transition table. As we can see that in the state transition table, we have a current state, we have input or event condition here, and then we have a next state. So when the present state or the current state is off, and if we press the speed button, then it will make transition to the low state as its next state. And if the current state is a low state, and if we press a switch, press the speed button again, then it will make transition to the high state. And when the current state is a high state, and if we press the speed button once again, then in that case it will go to the off state. So this example actually explains how a state machine or a finite state machine works. We call it a finite state machine because this machine has got finite number of state. So as you can see, there are three number of state. So that's why they are called finite state machine. Let's proceed to the next slide where we can see the type of finite machines. In principle, we find two types of state machine. One is called Mealy state machine and another one is called Moore state machine. So if we see a state machine in its block diagram form, then what essential thing we find is the presence of a state register, which can be combination of flip-flops. Variety type of flip-flops can be used. So, and there can be a combinational logic, which is called next state combinational logic, and there can be output combinational logic. So, uh, and then from the uh, state register, there will be a feedback to the input of the uh, next state combinational logic, and then the circuit input will also be applied to this based on some logic that has been implemented over here. The state register will receive the new inputs in synchronization with the clock, and then they will be passed on to the output combinational logic. Now, in case of Mealy machine, the output combination logic will be governed by two types of input, one coming from the state register and another coming from the inputs directly. And based on these two, the final output will be decided in case of Mealy type of state machine. But if we see uh, in Moore machine, the input is not directly connected to the output combinational logic. So that means output combinational logic decides based on the input received from state register only. There is no direct input from the circuit input or the state diagram input to the output combinational logic. This is the state diagram representation of the two finite state machine. Here we can see that uh, mm, this left side is the state diagram for milli state machine, and right side we have the diagram for the Moore state machine, milli state machine and Moore state machine. Here, the principal difference between these two is that uh, the state in case of milli machine is represented by different symbol like here S0, S1, S2 like that, and here also it is same S0, S1, S2, S3 like that. During the transition, as we can see, there are two figures. The first figure represents the input condition and the second figure represents the output conditions. So input and output in case of milli state machine in state diagram, it is represented like this. So as you can see that here also the first zero represents the input and the second zero represents the output. So is the case of other states also. But in case of Moore state machine, as we can see that output is actually based on the state. So state 0 will produce output 0 only. So since it is purely on the state dependent, so that's why the output condition has been included inside the state, and the input conditions are specified during the transition only. So this means that when the state machine is in state 0 condition and it receives uh, 1 as input, then it will make transition from S0 to S1, and then during that time its output will become 1 once it reaches to S1 condition, and this has happened because the input condition is set to 1. So uh, how the output condition is represented and in which place, from that we can easily understand whether it is a Mealy state machine or it is representing a Moore state machine. I'm going to talk about how to analyze a sequential circuit. In this slide, we will learn about that. Let us assume that we are given a sequential circuit as shown in this diagram. Over here, we can see that the sequential circuit is having two flip-flops and there is one input X. Clock is applied simultaneously to both the flip-flop. That means this is a synchronous sequential circuit, and there are some combinational part of it. And as we have discussed in previous slide, that input combinational logic and output combinational logic are part of the sequential circuits. Now, if we analyze this, we have got two flip-flops, uh, which is the flip-flop A and flip-flop B. Now, when we start analyzing, first of all, we will try to write the flip-flop input equations. Now, here we are using D flip-flop. So, first of all, we try to find out what are the input expressions to the flip-flop over here and at this point. So we will first find out. So here this is our DA. At this point, whatever we find, that is called DA, and in this point it is DB. It is DB. So DA, as clearly we can see that this is uh, coming from the output of an OR gate, and here the OR gate is having one input coming from the actual input of the circuit, that is X, and other it is coming from the output of the second flip-flop, which is referred as B. So this is referred as B. So here, as a result, we are getting dA equal to X plus B. Similarly, for the input of this flip-flop, we can see that which is coming from the output of this AND gate, and to the input of the AND gate, we can see that X is in inverted form, and output of the previous flip-flop, that is flip-flop A, is given as the another input of this AND gate, and as a result, the output expression of the AND gate is X AX bar, and which is the input flip-flop equation for DB. Now, next we will be try to find out what are the next state equation. That means the characteristic equation for these two flip-flops. As we have learned in the previous slides, that in case of D flip-flop, the output is equal to input. So here A plus is representing the next state of A, B plus is representing next state of B. So the next state of A equal to dA, which is equal to X plus B from here. So this is our next state for flip-flop A. Accordingly, this is our next state for flip-flop B. And this is the output equation. As we can see that in this uh, mm, OR gate input, we have one input coming from the flip-flop B output and another one is coming from flip-flop A output. As a result, the output equation y equal to A plus B means A or B. Now, from these expressions, we can work out the state table, which is another state or another representation of the given sequential circuit. What do we do over here? We write the present state. Here we have A and B, and we write the input. So these are our input parts, and based on the input applied to these expressions, we find out A plus, then B plus, and Y. So accordingly, they are listed over here. The first row, if we see, A is equal to 0, B is equal to 0, X equal to 0. So that means here, if we put these values, we will get A plus equal to 0. So that's why this 0 is here, this 0 is here. Then if we apply the same thing uh, at this input, so we will get 0 for this also. And during that time, since both of them are 0, 0, A and B, so as a result, output will also be 0. So in this way, if we work out the entire table for all 8 combination of the A, B, and X, we can find out this uh, state table. Next, we are going to discuss about how to draw the state machine diagram uh, for this Moore state machine. This is a Moore state machine. From the diagram itself, we can see that the output logic where we have a OR gate. So this OR gate receives two input. One is the output of the second flip-flop and another one is the output of the first flip-flop. There is no direct connection between the input X to the output logic. As a result, you can say that this is a Moore state machine. So accordingly, the Moore state machine state diagram representation is given over here. So if our present state is 0, 0, which is represented by this one, here our present state is 0, 0, it is called S0 also. Here the output condition is 0 in for both the cases. So you can see here that the output in case of Moore machine is being indicated inside the state itself. And if the input is 0, so it will remain in the same state. And if the input is a 1, it will migrate to the state 1, 0. Then if the present state is a 0, 1 and if input is 0, that means this is the condition. So then in the next state, it will go to 1, 0 and it will produce a output 1. So it will produce a output 1 and it will migrate from this state to 1, 0. So in similar manner, if we uh, see for the other entries in this state table, so we can see that the uh, the state diagram for this can be easily drawn over here. So when we uh, perform the analysis of a sequential circuit, these are the important phases through which we need to go through. We need to first work out the flip-flop input equation. Thereafter, we need to find out the next state equation. Thereafter, we find out the state table followed by the state machine diagram. And thereafter, we can explain the circuit operation, how the circuit works. So, accordingly, uh, we can explain over here. It has got four states 0, 0, 0, 1, 1, 0, 1, 1. When X is applied, the circuit moves from one state to the other according to the state diagram, that is this one. The output Y depends on the present state of the flip-flop A and B for the Moore state, and the next state is stored in the flip-flop A and B on the active edge of the clock. So if we see the flow diagram of the sequential circuit, here this block diagram or the flow diagram explains the identify the flip-flops. So here we can see that we have D flip-flops. Then write the flip-flop input equations. So here we have done that. Then thereafter find the next state equation. Here we did that. Then thereafter construct the state table. In this step we have done that. Thereafter draw the state diagram. So we also perform that over here and then describe the circuit operation where we complete this. So this is how we perform the analysis of a sequential circuit. Now we move on to another example where we are given another sequential circuit with D flip-flop only. So here, if we try to analyze this, again we find that here we have two flip-flops, D flip-flop. So this is flip-flop A, this is flip-flop A, and this is flip-flop B, and this is flip-flop B. And this is our input to the sequential circuit, and the output Y is available over here. This is our output Y. So the flip-flop input-output equations, as we can see that uh, here, over here, the equation will be like this. Uh, since in case of D flip-flop, the input will be equal to the output. So the expression over here and here will be the same one. That's why directly it is written AT plus 1. This is another type of representation. In the previous slide, we have come across A plus, and here we are representing it by AT plus 1, but they are representing the same one. So here we can see that the present state is of the state is for flip-flop A is represented by AT, and present state of flip-flop B is represented by BT, and next state of uh, A flip-flop is represented by AT plus 1, and next state of flip-flop B is represented by BT plus 1, and final output is represented by YT, or thereafter in a simplified manner it is Y. So now if we see what are the inputs over here, here it is A, and then this is, since it is A, so this is A, this is X, so here we get XA. So here we get XA. Similarly, here we get, this is X, and another input is coming from B. So here we get XB, XB. So accordingly, the output of the OR gate will be the input of this one, and the same thing will be available at the output. That's why AT plus 1, or the next state in A, equal to AX or XA plus XB or BX. So plus represents here the OR operation. Similarly, for the other one, it is A bar X. We can easily work out for here it is A bar X, and then the final output, as you can see that uh, the output of the sequential circuit Y over here is basically we can see that it is X bar, and then this input is X bar, this is X bar, and the other one is coming from the output of the OR gate, and to the input of the OR gate, as you can see, we have a and we have a B. So A or B, and then it will be ended with X bar. So this is how we worked out the flip-flop input equations and flip-flop output equations. Now we uh, work out the truth table, sorry, state table, as has been described over here for the from the flip-flop input-output equations. So here, as you can see, that here also we have got two flip-flops and one input. So like similar previous one, we have present state A and B and input X. So this is our input side, and then the next state that is A t plus 1 and B t plus 1. This is represented by the next state, and then the output expression is like this. So if we place all the values over here, the different conditions here, and we will find that the next state values, and that is A and B, and the output values are being determined. So based on this, now we can find out the state diagram. Here we can see that this is another form of another representation of the state table. Uh, this is showing another representation of the state table. Here, the the first two column represents the present state A and B, and in the next state, as you can see that uh, x equal to 0 and x equal to 1. For that, two different conditions occur. So the table length has been decreased to half, and the output is also again two different condition occurs. So that is for x equal to 0 and x equal to 1. So this is the same, I mean, same state table, but another representation, uh, which is in compact form. And thereafter, from this table or from the previous table, we can draw the state diagram. Here we can see that, first of all, our present state is 0, 0. So that is being represented over here, this state. And if our input is 0, then it will remain in the 0, 0 state. So if our input is 0, it will remain in the same state only. And during that time, the input is 0 and the output is also 0. Input is 0 and output is 0. Now, when we are in state 0, 0, and if we have applied a 1, then what will happen? We will make transition from 0, 0 state to 0, 1 state. As you can see that we can make a transition to 0, 1 state. But during that time, again, the output condition will be 0. So input is 1, but output is 0. So in this way, we can draw this state diagram from the state table. And if we talk about the final action, final analysis, that circuit operation, so we have to compute the next state. Combinational logic circuit determines the D input from the present state and input X. Then we store the next state on active edge of the clock. The D flip-flop updates the next state, and thereafter, based on the expression, the output will be generated, and which is actually based on the present state and the input condition. So the same analysis of sequential circuit. Now we are looking this from the different flip-flop, that is JK flip-flop in this example. So this is flip-flop A, and this is flip-flop B. So over here, as you can see, uh, there is again input X, and it do not have actually output combination and logic. So A and B are our direct outputs, and here we have to see what are the input conditions. This is flip-flop A, so that's why this flip-flop input J is attached with a subscript A. So JA, you can see in JA it is the B. That means the output of the second flip-flop is connected as the input of this one, and KA is actually combination of X bar and then B, X bar and B. Similarly, JB is X bar, as you can see that this is X bar, and KB is KB expression is actually coming from the output of an XOR gate. So to the input of XOR, we have one input coming from X and another one is coming from A. So that's why it is A XOR X. So these are the flip-flop input equations. In case of uh, JK flip-flop, uh, the input output expressions we already know. So here the outputs will be AP plus 1, that is the next state, will be J. If we remember the previous, characteristic equation, so over there we find J Q bar and Q bar, K bar Q. So here Q is replaced by A, so that's why this expression becomes like this. So then wherever we get J, since we are doing it for the flip-flop A, that is this is flip-flop A, let me write over here, this is flip-flop A and this is flip-flop B. So first of all, we are writing the expression over here, that is A P plus 1, that is J A bar, uh, and here A bar is same and J means it is B, so that's why J is replaced by B, and here K bar, K means it is B X bar, so B X bar and then a bar, overall bar, and then A. So if you expand it, you will get this expression. Similarly, for the uh, second flip-flop, that is flip-flop B, so we can find that this we can arrive at this expression. So we have come across the flip-flop output expressions. So from there, we can state table as like the previous examples, we can find out the expressions, and thereafter we can find out the flip-flop inputs based on the state table, and from here we can work out the state table, state diagram as has been done in previous cases. Uh, like for example, if we are if our present state is 0 0, and if we apply a 0, then we will migrate to the state 0 1. So we are in present state 0 0, and if we apply a 0, so then we will migrate from here to this state, and in during that time our output will be uh, actually here there is no output combinational logic, so the flip-flop status only can be treated as the output. So that means the flip-flop output conditions for A will be equal to 0 and B will be equal to 1. So in this way, this state diagram has been designed. And regarding the circuit operation, obviously the input logic, the input X is inverted, and along with the present state A and B generates the JK flip-flop excitation signals, as we have analyzed in this one in the previous slide. The state update on each active clock is both JK flip-flop update their output simultaneously, and the feedback, the new output A and B are feedback to the combination logic to determine the next step. So this is these two slides shows how to analyze a sequential circuit constructed out of flip-flop. Then this is the example of the uh, sequential circuit given for analysis with P flip-flop. The approach is similar. Again, we are given with a sequential logic circuit where the flip-flops, there are two flip-flops, and they the two flip-flops is are of T flip-flop type. So we know the flip-flop input equations from here. Then thereafter, using this, we can find out the output expressions over here and here, and we can find out the output expression y. Okay, y will be in this case, y will be equal to, just a minute, y will be equal to y will be equal to uh, that is uh, a and b. It is simply a and b, a and b. So these are the three expressions based on which we can make the state. Here is the state table, and from the state table, we can make the state diagram. This is also a more type of state diagram. Whatever we have learned in the previous from the previous slides, so same is applicable over here. So we can easily convert them in the state diagram. So finally, we come to the end of this lecture. Here, let us try to provide the summary what we have learned. Here we have discussed about the flip-flop fundamentals. We have talked about the operation, characteristic equation, state diagram, then excitation table for SR flip-flop, JK flip-flop, D flip-flop, and T flip-flops, highlighting their roles as basic memory element in sequential circuit. We talked about finite state machine, explain the concept of the finite state machine and distinguishes between Mealy machine and Moore machine with examples uh, uh, having state transition and output generation. Then we analyze the sequential circuit. Uh, we learn how to systematically analyze sequential circuit using uh, state tables, state diagram, flip-flop input-output equations, and how the next state and output can be decided. And then the same analysis we did for all types of flip-flops, rather D flip-flop, JK flip-flop, T flip-flop, etc. And that's how we developed a very sound understanding about how to analyze a given sequential circuit using the techniques like uh, the state table, state diagram, and flip-flop input-output equations, etc.